Good morning, everybody. Okay, we're going to continue in the Chapter 4 notes where we left off. Today we'll be starting with Newton's third law of motion. Okay, now if you'll remember, the first law of motion, also called the law of inertia, was the one that you remember for every, a body at rest will stay at rest, and a body at constant speed stays at constant speed as long as the net force acting on it is zero. There can't be anything left over to change the motion. But if there is something left over, then we go to Newton's second law, which says that if you do have a force left over, it will make the mass accelerate. It will overcome the inertia and change the motion. Now, Newton's third law of motion. Sometimes you'll see this one called the action-reaction law. And you probably remember this one quite well from middle school, okay? It's the one that says for every action force, there's going to be an equal and oppositely directed reaction force. So that's two things it has to be an action-reaction pair. It has to be equal and oppositely directed, okay? If you apply a force to an object, the object will exert an equal and oppositely directed force back on you. Now, if the object of focus exerts a force back on you, is that part of the net force we look at? No, it isn't. Remember, that is the object acting on you. You're not the focus object. So when we look at an object and the forces acting on it, we don't look at the forces that it exerts on other things, because that has nothing to do with the motion of the object itself. So only the forces that act on the object from others are the forces that we look at in a problem. Now, in order to begin understanding the forces, the different types of forces, and how they work together, we first have to learn how to diagram these forces properly, okay? So we're going to be learning today about free body diagrams, or I like to call them FBDs. Free body diagrams. These are diagrams drawn to show only those forces actually acting on the object in question and the directions they point. Okay? So, that's why in this class you don't have to be an artist. We're not going to have to draw the horse pulling the wagon. We're not going to have to draw the rockets, the cars, the trains, the planes, all that fun stuff. You don't have to be an artist in physics, because with a free body diagram, you don't actually draw the object, okay? So I'm going to show you how to do that, but there are some rules we have to follow when we're doing a free body diagram. And let me tell you, on the AP exam, they can be a real stickler about free body diagrams, so I'm going to be talking about a few things. First off, when we draw a free body diagram, we only draw the actual forces acting on the object of focus. Okay? If the object of focus is pushing back on something else, we don't care about that. We only care about the forces acting on the object itself. All right, the next one. We do not draw the net force. The net force has no place in a free body diagram. The free body diagram is for the individual forces that make up the net force. It is not for the net force itself, okay? So only the individual forces that make up the net force, not the net force itself. Also, we do not draw components. unless you're specifically asked to. We do not draw components. You draw components on the free body diagrams on the exam, and they will deduct points for having extraneous force vectors. All right? So never draw components unless asked to do so. Every once in a while, they will ask you to draw components, like maybe for the weight on an incline or something, kind of like what we did with acceleration on an incline. Now, the next thing you need to know is that we do not draw kinematics vector arrows. Okay, we do not draw kinematics vectors like D and V and A, again, unless asked to do so, because a free body diagram is for the forces. It's for the dynamics, and these aren't dynamics, they're kinematics, okay? So unless you're specifically asked to draw a particular kinematics arrow on a diagram, you don't do it. Finally, label, again, label. Unlabeled vector arrows do not earn points on the AP Physics exam. If they are unlabeled, then they may as well not exist on the paper, okay? No labels, no points. That's the way it is. And there's actually one more thing you need to be aware of. When we draw a free body diagram, we draw a dot to represent the object. This is why we don't have to be an artist. And we draw the forces coming from the object. Now, they're not really coming from the object. They're more like acting through the object. For example, we would draw gravity from the earth pulling straight down on the object like this and label it as gravity, F sub G gravity. If you have somebody pushing to the right with some applied force, okay, we would draw it to the right. We wouldn't draw it back here pointing into the object. We point it away from the object. And we would label it as an applied force, okay? So the arrows must be drawn coming from the object in their appropriate directions, and the arrow must touch the dot. That's been an interesting development in the last few years, that they've asked that teachers make sure that students are connecting the arrow to the dot representing the object. They are not counting them if they don't touch the object. Strange, I know, but that's what they want, so that's what we practice and make a habit of. We draw the arrows coming from the object and make sure it's attached to the object's dot. Okay, so now these are the rules that we're going to use to draw free body diagrams. So now let's actually draw some free body diagrams. Bam! It's like magic, isn't it? All right, so I've got some clean paper here that I'm going to diagram on, and if you want to copy these down, you may. You might want to get another sheet of paper to do that on, unless the back side of your printout is blank, and then you could just flip over and do it on the back side. So, first off, when I have an object that I want to draw a free body diagram for, we start with a dot, okay, to represent the object. And then we draw the arrows and label them. We draw them in their proper direction, coming from the object and attached to the object. Now, we need to have a situation first on what's going on. So let's talk about, I don't know if you all remember from our last set of notes, we talked about a hay wagon, okay, with hay in it. Okay, so here's a hay wagon, and it's being pulled by a tractor or a horse, whatever, along the track, okay? Now, we don't have to be an artist and draw that. That's ridiculous, and it just gets in the way, all right, of the arrows. So let's just think about that picture for a minute and what is actually acting on the wagon as it's being pulled along the road. Well, whenever I have an object that's on a surface, or whenever there's a surface, I like to make sure I know the orientation of the surface in my diagram by simply creating a dotted line. Okay? So there's the surface. Now we can orient our arrows. First off, we know one thing that always acts on any object that's on Earth is gravity from the Earth, pulling down, straight down to the bottom of your paper every time. It never points at an angle somewhere else. It always points straight down to the bottom of the page, just like this. And then we label it the gravity. So that's acting on the wagon, okay? Now, we also know that the wagon is being pulled by a tractor or a horse. Whatever it is, it's an animate object, and it's acting on the wagon, and we call that an applied force. In this case, if pulling to the right, there we go, applied force. Okay? All right, now let's talk about another force. Let's talk about normal force for a minute. Normal force is a force from a surface pushing back on an object. In this case, we have the surface of the road. Now think about it. The reason the wagon is not sinking into the road is because the surface of the road is pushing back up on it, supporting its weight, its gravity. So we can show the normal force from the road pushing back up like this. Normal force we indicate with a capital N. And I'll explain why we say capital N instead of F sub N later, okay, when we get to talking specifically about normal forces. There might also be some friction between the wheels and the road. Friction always opposes motion, so we draw it this way, like that, friction force, okay? So there's 4 symbols right there that you need to know, okay? Normal force from a surface, we use a capital N. Gravity or weight acting on it from the earth, we use FG. You could also use a W, same thing, all right? Friction, okay, friction, we use a capital F, subscript F. All right, applied force, we use an F sub A. Now there's one force we've not actually talked about yet, and that would be tension. And interestingly enough, like normal force, we don't use an F with a subscript. We actually use a capital T for tension. Okay? Let's look at an object that has tension acting on it. All right? Let's suppose that we have, let me think of something here. Okay, let's suppose we have a lantern that is suspended. All right, a little lantern that is suspended by 2 cables, okay? Maybe inside a tent or something, all right? And we want to draw the free body diagram of what's acting on that lantern. So we draw a dot for the lantern. And the first thing we always do after we draw our dot is draw its gravity from Earth, its weight. Because as long as you're on Earth, that one exists. Gravity never turns off, so that's always there. Now, what else? Well, there's no surface touching the lantern, so there's no normal force. You don't have surfaces moving against each other, so there's no friction. And no animal, person, or animate object is pulling or pushing on the lantern. It's just hanging there. But we do have 2 cables. And in cables, we have tension. So we have one tension that pulls back along the cable. Tensions always pull back along the cables and strings. Okay? And then this one right here is going to pull the other way, like that. All right. Now, technically, when you have forces that you're drawing, notice I haven't talked about the lengths of the arrows, but when you're drawing these arrows, technically, the lengths of the arrows should be proportionate. For example, if you know that one tension is larger than another, you would draw that arrow a little bit longer. If you know one arrow force is smaller than another, then you should draw that force smaller, if you get the idea, okay? Now, those are two pretty good examples right there. Let me show you what your assignment is going to look like for this. And I'm going to work a couple of them with you and to help you get started on it. It's actually kind of fun when you get into it, and it's not terribly difficult. But practicing different situations with different forces is extremely important, and that's why you're going to see so many of them. We're going to have lots of free body diagrams, and I do mean lots. So this is the front page of the assignment that you're going to be working on with free body diagrams. I call it a day in the life of a physics rock, because the majority of these on the first few pages show a rock in some kind of physical situation, and you're going to be drawing a free body diagram on the outline of the rock that's right next to it in the square, okay? So this is where we're going to draw our free body diagrams. And in fact, they have one right here already drawn, and we can go ahead and label it if you want, okay? It shows a rock static. Now, static means stationary. Keep that in mind, stationary. Kinetic means moving, but static means stationary. So this rock is static at rest, and it's got a string pulling up this way and a string pulling sideways. So that's why it has one arrow pointing back along this direction, back along the string away from the rock right here. So that is a tension. And the other one points back along its string right there. There's another tension. So what is this one? Well, we're on Earth. That has to be the gravity. Okay? So now that one's labeled. This one I think you can do simply enough yourself. You've got a rock just hanging at rest, so you've got a string, and it's on Earth. So I think you can handle that one. I would like to look at one that's a little further down. Let's see here. One of these right down here. Let's look at number 7 for a minute, okay? Now this is interesting. There's an incline right there. The rock is sitting on the incline. That means the incline has to be pushing on the rock. All right, so the first thing I'm going to do to orient my vectors more easily, I'm just going to draw a little dotted line so I can see where my incline is. I'm drawing it parallel to the incline. And this will help me draw my vectors, okay? So let's take a look at what's happening. First off, we're on Earth, so the first thing we should always draw is gravity. There we go. Now, do we have a surface touching the rock? Yes, we do, the incline. The incline is pushing that way on the rock, not straight up, guys. Normal forces always push perpendicular to the surface. The surface is pushing that way on the rock. It can't push up because it's not facing up. It's facing this way. So we draw the normal force perpendicular to the surface every single time. Perpendicular to the surface. We also have a tension. A string is right there, so we have a tension. Now, which way is the string pulling? Well, notice the rock isn't sliding down the incline, so the string tension is what's keeping it from doing that. It pulls back along the string up the incline. There we go. That's it. Just those three. Now, can you have more than one tension? Well, of course. Can you have more than one normal force? Yes, you can. Here I have two surfaces touching the rock. One surface faces up that way, so it pushes that way. The other surface faces that way, so it pushes that way. You can have two normal forces. All right? Let's look at another one. If I turn over and look at this one, okay, the one that really freaks people out between these two, and they're almost identical, is this one, okay? They see that the rock is sliding at constant speed without friction. So let's take a look. The rock is moving to the right because here's where it used to be, all right? So it's moving to the right, and it's on a surface, but there's no friction between the rock and the surface. That's nice when you can do that, an ideal situation. So let's look. Gravity first. Boom. And you have a surface. The surface is facing up, so it pushes up. In fact, notice the rock is not moving up or down, so these two have to balance, which is why I drew them the same length. Since the rock is moving to the right instead of up or down, those have to balance. There can't be anything left over, otherwise the rock would move up or down. Now, the rock is moving to the right. People always want to draw an arrow to the right. Why? Is there anybody pushing the rock? Is there anybody pulling the rock in the picture? Is there a string attached to the rock pulling it? Are you starting to get the idea? The reason the rock is moving at constant speed is that there's nothing in the plane of motion to change the speed. Without friction, it won't slow down. So it continues at constant speed to the right because there's nothing there to change the motion. Now are you starting to get the idea? I hope so. One more I'd like to look at real quick is right here. An object that has been projected so that it travels a parabolic path. Now, I want you to notice the rock is already in air. Nobody's touching it. There are no strings. There are no surfaces. The rock is in mid-flight and it's moving upward. So, what's acting on the rock? Well, we have gravity, obviously. The earth never turns off. Are there any tensions? Nope, no strings. Are there any normal forces? Nope, no surfaces. Are there any frictions? No, because when we have an object like this, unless specifically stated otherwise, we ignore air resistance. We're looking at an ideal situation here. So, the only thing acting on the rock is gravity. It's basically in free fall. It's slowing down as it moves upward due to gravity. So it's basically in free fall. Get it? I think that's kind of cool. Okay, I've done a few of these, and now what you're going to be doing is practicing them on your own. Have fun with it, okay? Bye-bye.